So let's talk about the running time for the Bellman-Ford algorithm. All right. So this is the Bellman-Ford algorithm here. So we start off by creating a input adjacency list to the Bellman-Ford algorithm. While most cases you could assume either getting in the in list or the out list. Well, we're just going to assume that it's far more common to be only given the adjacency list. So sometimes you do have to calculate the input adjacency list. And then what do? We do the same thing as before. We say that the shortest distance using k hops is either equal to the shortest distance using k minus 1 hops, or for every vertex in the graph, but we don't need to look at every vertex. We could just look at the edges that are going into a particular vertex. For every edge going into a particular vertex, then recalculate the potential new distance using a kth edge, using that edge, and then see what the minimum value between these two is. Okay? And if we do this calculation, we get the minimum value, the minimum distance to get from S to V using at most k hops. Okay? And then again, for every time we initialize a new row, we copy all the values from the previous row into the new row. So the question is, how much time does this take? Well, this right here takes O of m plus n time to create the in list. This takes O of n time. And this, we have n minus 1 iterations. So this takes O of n iterations. Or let's say, I'm not going to even do O of n. I'm just going to say it's n iterations. Because we're saying that the number of hops could be at most k minus n minus 1. And then we're going to have basically these two loops here. So what do these two loops here result in? How many iterations do these two loops result in? Well, we're saying for every vertex, we look at the input edges to that vertex. Okay? So we're not looking at all the edges every single time. We're only looking at the input of edges for each vertex. So what do these two together equal? These are all the edges in the graph, O of m. And if there are very sparse a number of edges and lots of vertices, then you have to consider that this work becomes significant. So you have to do O of m plus n work. Okay? And each of these take constant amount of time calculation, O of 1. Okay? So the running time becomes n times O of m plus n. Okay, makes sense. Makes sense. What about the space? Well, the space we saw in the previous table, we saw the space take O of n squared. We saw an n squared table, and we also include this term for the input list. This is for the input in the NV list, and this is for the Bellman-Ford table in example. But wait, you might say, do we actually need to consider that whole table? Because remember, when we were going through the example, we were only referring to the row directly above the k minus 1 row or a calculation, right? We never looked at the earlier rows either. We only were looking at the k minus 1 row. So we don't really need an n squared table. So we could greatly reduce our burden by not having a table and not copying one row to the next every single time. We don't have to do that. We could just have a single row. Either it stays the old value or it changes to a new value. Right? So we could reduce this algorithm further by simply keeping a single row and doing exactly the same calculation. And you get exactly the same results, right? You get exactly the same result. You say for every edge here in NV. So this takes O of m iterations. And then you say n iterations here. And then you, of course, have to recalculate the input, the NV. Calculate. But wait, do we really need to calculate this? Can't we just go through every edge? Can't we just go through every edge? Do we really need to do these two for loops? Isn't these two for loops just saying go through every edge in whatever, go through every edge in whatever order and try to see if adding a kth edge would make the distance shorter? Yeah, right? So we don't even need the NV list. So we could just get rid of it. Instead of these two for loops, we just say for every edge. For every edge, do this calculation and change the distance if adding this edge as the kth edge in the shortest path to V reduces the distance. And in fact, that's exactly the optimized form of the Bellman-Ford algorithm. This is the cleanest version. Okay, so it's beautifully simple in the end. We went from something complex and we whittled it down to its core code. And the beauty of the core code is that everything is beautifully simple and that this algorithm can handle edges with negative lengths. Okay, and it's built upon the fundamental assumption that you aren't just adding a vertex to a set and saying, okay, I've calculated the shortest path to this vertex. No, you're doing a recursive analysis. You're saying every vertex the entire time could be updated at every iteration. Every vertex could be updated. So what you're really doing now is simply updating, continuously calculating the shortest distance for every vertex, assuming the number of edges that you could take is more and more and more and more. Okay, beautiful way to use recursion. So that's the Bellman-Ford algorithm. We're going to discuss some details about the Bellman-Ford algorithm next. Thanks.